All right, everybody, problem number 3. This is where it really does step it up a notch. Um, Here's the reason why. If you look at this problem, it's asking you what's the simplest form of not one radical expression, but actually two radical expressions multiplied together. So essentially, it's taking the exact same concept that you had to do right here, that I kind of helped guide you through, and end up with this answer right here in the box, but yet have to do it now while doing multiplication. There's one potential pitfall that could very easily happen to some students depending on their point of view. What some students might choose to do is try to simplify one of these first. Like, for example, try to simplify this guy. Figure out what that answer is, much like you did on problem number 2, and then hit the reset button, figure out what that guy is, simplified, write that one down, and then try to multiply them together from there. I do not advise you to do that. Let me show you why, and let me show you why it's a similar situation with fractions. Let me clear out all this junk. So when you look at a problem like this, if you look at fractions, and suppose I wanted you to take 72 divided by 81, multiply it by 24 divided by 18. Many of you probably would not want to go this route and do top times top, because then you have to get a large number and bottom times bottom, ending up with a really large number. Ultimately, it wouldn't be that big deal when it comes to calculators, because then all you'd have to do there is just simplify your fraction and away you go. Most calculators now make that a pretty painless process. What many of you would probably prefer to do on this problem would probably choose to reduce each one individually and go in this direction. Oops, that'd be 9 times 9. And then have that be 8/9, and then do the same thing here. Let's write that as 6 times 4 and 6 times 3, and simplify that fraction, write that as 4/3. And then many of us would probably much prefer to do the problem this way. And there you have your simplified fraction like that. That approach of you doing this guy individually and that guy individually and then multiplying the results together works great with fractions, but does not really end up with that happy of an ending when it comes to doing it with radicals. The only reason why that happens is sometimes you have to simplify radicals within radicals, and honestly, it becomes way more of a mess than what you probably are willing to deal with. So, I really do appreciate the way the textbook approaches this problem. So, to lay us some foundation about what they're doing here, first, take a look at this here in blue. Review. We know that when we take a radical of a quantity and multiply it by the exact same root of another quantity, we can multiply those two together under the same radical. So this works no matter if they're square roots or cube roots or fourth roots, whatever. In this case, they are square roots. So in here in this little tan box here, it makes sense to me that they're using that blue property properly. That's fun to say really fast. And multiply the two quantities together. Now, the reason why they end up with x to the fourth and y to the fifth is because of that review property that you see right there in red, right? Remember, when you have the same base, you can take the two exponents and add those together. What's going on right there when you have x to the third times x to the first? It really is x times x times x times x, which is another way of saying x to the fourth right there. And the same thing happens with those y's, right? 2y's multiplied together times 3y's multiplied together gives you a total of 5y's being multiplied together. Now, do me a favor, scribble out those next 3 lines right there. Number 1, if you look down at that third line there, there's absolute value. And what we're going to do here, the same thing as before, is we are going to assume that the variables that we are working with are positive. Okay? And if all these variables are positive, we don't have to worry about any absolute values here. Here's why I scribbled out these other 2 steps. Remember in previous lessons why I had you guys approach this problem and how you would want to approach this problem is let's approach this in 3 different stages here. Let's take the square root of 720 and split that apart using perfect squares. Let's take the square root of x to the fourth and let's take the square root of y to the fifth. Okay? Now that square root of 720 could get a bit messy. Reason why is because it's very large, right? X to the fourth is a nice one because that exponent's even. Y to the fifth is odd, but then we can deal with that one the same way we dealt with in problem number 2. Now that 720, what you're looking for, since 720, last time I checked, is not a perfect square. Let's go ahead and verify y, right? We take the square root of 720. Bummer alert, decimal. But if I can find a perfect square that goes into 720, like say, I don't know, 144. I'm going to be real with you. I've had to do this take maybe like 5 or 6 or 7 times to get this right. So pardon me if I'm going to try not to play like the dumb guy here and just pretend. And I'm just going to, let's just remember that I've done this maybe like 5 or 6 times, and I'm trying to get to the end of this as quickly as possible and not have you guys watch a video all hour long. So the biggest perfect square that can go into 720 is 144. And that goes in there 5 times. I will say this though, we do have the biggest perfect square of 144 because if you look at that 5, there are no other perfect squares that go into that 5. So back here at our problem, we can now split apart that 720 into 144 times 5 times that 5. That square, that x to the fourth, we're going to leave it alone because we can take the square root of that. It's already a perfect square, just like 144 is a perfect square. But y to the fifth is not a perfect square. But we can split that up very much the same way. Flip back, take a look, see how we handled that x to the 7th here. And we took that x to the 7th and split it apart as an even exponent times one odd exponent with x to the first. So that way we can take a cube root and come up with that answer pretty easily. We're going to do the exact same thing here. So the biggest perfect square that I can take a square root of when it comes to those y's would certainly be y to the fourth. And let's multiply by one more y. Okay? So let's highlight our perfect squares here that we actually are going to take the square roots of. 144, the x to the fourth, the y to the fourth. Okay? We do those. We get 12, right? We get x squared, right? And we get y squared because all of these are positive, no absolute value signs are needed. And then take a look at what's still underneath the square root. We still have a 5, and we still have a y. And if you glance right down here at that final answer, we have the exact same thing. I would love it if you did the problem right here the way you see it here in blue. Okay? So let me guide you through this problem right down here. Trust me, once again, the whole thinking behind this is that it is a good idea to do it this way. Let's get that really large number because we can work perfect squares and large perfect squares to simplify that answer. Okay, so yes, I know it's going to get pretty ugly here, but let's do the 45 times the 35. I've done this enough takes where I actually know the answer, but I will still humor you and actually type this in. 35 times 45. We get 1,575, right? So that's our first value that we get here. Let's use our exponent properties and get the rest of this stuff, 1,575. And then remember we have x to the 5th times x to the 1st. So shouldn't that be x to the 6th? And then y to the 3rd and y to the 4th should make y to the 7th. Okay? So now here comes the fun part. The real fun part is trying to break apart that 1575 into two numbers and we want the largest perfect square possible. With numbers as large as this, don't try to worry about trying to find the largest perfect square possible. Just think of any perfect square that will go into there, and I can show you some tricks on how to whittle it down from there. For example, what's one thing that we know about 1575? It ends in 75, which I can think of a perfect square that can go into a 75, and that would be 25. So let's go ahead and take this answer. Let's take that 1575. Let's divide it by 25. Look what happens. We end up with 63. Okay? Here's a blast from the past. I'm going to take that 1575. I'm going to make a factor tree out of it. I'm going to put that over here. So wouldn't this be true about 1575? 1,575. I could now just factor that into two numbers, 25, which is a perfect square, times 63. Now, did we find the biggest perfect square of 25? Is there another perfect square that could go into, or a bigger perfect square that can go into 1575? Yes, there is. And the clue is in that 63. Couldn't we factor 63 into two numbers where one is a perfect square? Yep. It'd be that 9. I think 9 times 7 is 63, right? And so here's a fact, Jack, is that 7, there are no perfect squares that go into 7. So I think we're good to go. So another way of us expressing 1575, couldn't we call it 25 times 9 times 7? Or couldn't we really call this, and I'll write the result over here in blue, 1575, 1575 can be written the same as 225, think about where I got that from, times 7. Didn't I just get that by multiplying those two numbers together, 25 times 9? And if I do 225 times 7, I will get 1575 times x to the 6. I'm going to leave that one alone, right? Because it's pretty easy to take the square root of an even exponent. It is not easy to take the square root of an odd exponent, but I'm going to break apart that y to the 7th into, you guessed it, y to the 6th, just 1 degree less. So that way I can just do y to the 1st right after that. So let's get some perfect squares going here. 225 is a perfect square. X to the 6th is a perfect square. Y to the 6th is a perfect square. Let's write those perfect square. Let's write the square roots of each one of those. So I'd have 15. Square root of x to the 6th would be x to the 3rd. Be careful. And then we'd have y to the 3rd. And then we'd have our square root of 7 times y. Be careful about how you write that square root in relationship to that 3. Don't let this 3 kind of drift this way, because then wouldn't this be saying something else? Right? Kind of looks like a cube root, doesn't it? We don't want that. So make sure that you do a good job of separating that third power from that square root. A lot of students like to cover their own you-know-whats by just putting a dot right there, a times dot, so that way they know that I won't misread what they write. Okay? And there's your final answer right there. Okay? So that's how these problems go. You will have to deal with this at a certain point on this test. Okay? Thinking of tossing one of those on your second quiz, so be prepared on it to work through that a little bit and get really good at that before you take the test. Okay? Let's move on to problem number 4 in the next video here. What I can promise you about problem number 4, it's definitely not any harder than problem number 3. I won't say it's easier, but it's definitely not harder.